Good afternoon to my viewers. What I'm going to suggest at this time as we begin section 10.2 on rational numbers as exponents is to pause the video to get these properties down. But as you copy these properties, I will tell you that it's probably a good idea to leave some room to the right, as I'm going to provide a few examples to clarify exactly what these properties do and how these properties work. So if you haven't done so, please take time to pause the video and go ahead and do that. Otherwise, I'm going to keep going here. So we are taking a look in section 10.2 as rational numbers as exponents. And what this essentially means is that we're going to take a look at not whole numbers and exponents anymore, but we're going to take a look at fractions and exponents. Now, we do have three laws that apply here for rational exponents. And then from earlier chapters from Math 90, we have the rules for general laws of exponents. And to bring more clarity to this, I'm going to provide some examples of exactly what this is going to mean. So let's say here I have a to the 1 over n. I can write a to the 1 over n as the nth root of a. So let's provide an example of this now. And let's say I have 64 to the 1 over 3. Well, if I have 64 to the 1 over 3, I can rewrite this, if I choose to, as the cube root of 64. Now, because this is 1, there's no exponent on this. We'll kind of see that a little more clearly in example 2. And the cube root of 64, well, that's equal to 4. Why is that? Because 4 times 4 times 4 is equal to 64. So we're asking ourselves, what number do we multiply by itself 3 times to get 64? And that's going to be 4. So this is kind of our way of working backwards from exponents. So taking the cube root of 64 essentially undoes the work that's done when I take 4 and I cube it. So if I take 4 and I cube it, I get 64. Well, that means that the cube root of 64 is the opposite operation to this, which will give me 4. So that's just an example to provide for that. We'll do something a little similar here, and that is to say that a to the m over n equals n, the nth root of a to the m. Now, m can be 1, but that would just kind of provide the rule that we have in number 1. So let's just take a look at another example, quite similar to the one we just did. We're going to look at 64 to the 2/3. So in this case, the only difference here is that the value on the top is going to be 2 instead of 1. So we're going to go ahead and rewrite this as the cube root of 64 squared. Now, one way, it doesn't matter if you square 64 and take the cube root, or if you take the cube root of 64 and then square it. My recommendation is to always go with the root first, because it's going to be easier to take the root and then perform the operation on that than to take a number like 64, which is going to be incredibly large, and then find the cube root. So one way that we can express 64 to the 2 over 3, and that's going to be using a property down here. I can take, actually it's going to be this property right here, number 3, is I can take 64 to the 2 over 3, and I can rewrite that now as 64 to the 1/3 times 2 over 1. And what I'm doing basically is I'm taking 2 over 3 and I'm rewriting it as 1 over 3 times 2 over 1. And what I'm going to go ahead and do is I'm going to find 64 to the 1/3 first. When I do that, that's going to give me, well, 64 to the 1/3, as we mentioned above, that's equal to 4. Now, I still have this 2 over 1. But really, 2 over 1 is just 2, so I can write that as 4 squared. And that's going to now give me 16 for my final answer to that problem. So 64 to the 2/3, I can express as the third root of 64 squared, which I can go ahead and write in this form, split it up, take the third root first before I take the second exponent on the top, and get my final expression of 16. So we're going to take a look at rule number 3 now, at a to the m over n. We did look at this in our section in chapter 7 about how do we remove a negative from here. And all we did is we took the quantity that was here and we move it down below. So let's just kind of highlight an example of what this is going to look like. So suppose I have 64 to the negative 4 over 3. Now, yeah, I can go ahead and work on this. Well, the first thing I'm going to do, like I've instructed you before, is to get rid of the negative. So what I'm going to do then is just simply write this as 1 over 64 to the 4 over 3. So I'm going to have 64 to the 4 thirds. Now I'm going to go ahead and leave it like this. I'm not going to bother to introduce a fraction here because we were showing what this looks like in fractional form because some answers contain, or radical form I should say. Some answers contain, or some questions contain radicals, and you need to be able to go from radical form to using a rational exponent. So how do we work with something like this? Well, I'm going to write this as 1 over 64 to the 1 over 3 times 4 over 1. If you multiply 1 over 3 times 4 over 1, that'll give you 4 thirds. But what I'm going to go ahead and do, and if you need to pause the video to write this down twice, please do. I'm going to go ahead and solve that first. As we already know, that's going to be equal to 1 over 4. And since we have 4 over 1 here, I can just write this as 4 to the 4th. And if you check your work, you can see that 4 to the 4th is equal to 1 over 256. So this is how I perform that question. So we have three things we're doing with rational exponents. One, we need to be able to rewrite them in a radical form, as we're doing in the first two steps here. The second thing we need to be able to do is to figure out how to use the root in the exponent component of the rational exponent, the root being below and then the exponent being above, to take the root of the number and then raise that number or resulting number to an exponent. The third thing we need to be able to do with a rational exponent is to be able to take this response here, or this number here when it's raised to something negative, and move it below to make it something positive and work with it in the denominator. So that's the work we have to do with rational numbers as exponents. So now we're going to go ahead and visit just some general laws as exponents that you should have learned before. But if you've forgotten them, we'll go ahead and review them before we do a bunch of problems that involve utilizing these operations. So if I have a to the m times a to the n, this is equal to a to the m plus n. Let's explore why this is the case. So we're going to take a look at an example of this. Suppose I have 2 to the third times 2 to the fourth. Well, 2 to the third, okay, I'm going to put a big multiplication symbol here. We're going to use that later. 2 to the third, I can introduce as 2 times 2 times 2, because it's basically taking 2 and multiplying it 3 times. Now, big multiplication symbol here. So 2 to the fourth I can write as 2 times 2 times 2 times 2. Now all of this is getting multiplied together. I don't need to make this big. I just do this to illustrate how this quantity here represents the value of 2 to the third. This quantity here represents 2 to the fourth. When I combine these together, this is going to give me 2 times 2 times 2 times 2 times 2 times 2 times 2, or 2 to the seventh. Hence why we could also write this as 2 to the 3 plus 4 by simply adding the exponents. So this is just an illustration of why this property works. I don't expect, in fact, I don't even want to see you executing this each time. Simply add the exponents and take advantage of that property. Let's take a look at property number 2 now. A to the m divided by a to the n equals a to the m minus n. So when we multiply a common base, we add the exponents. When we divide a common base, we take the difference of the exponents. Let's take a look at another such example. So let's say I have 2 to the fifth divided by 2 to the fourth. Well, what this looks like algebraically is 2 times 2 times 2 times 2 times 2 on the top. On the bottom I have 2 times 2 times 2 times 2. And after the work that we've done in Chapter 7 on reducing, we should see here that we'll have a bunch of reduction here, leaving me with just 2. Now, you'll notice here that there's no exponent that we have on this. It doesn't mean that there is one. We just don't usually put it because it's not necessary. This will provide us with an exponent of 2 to the first. So please keep that exponent in mind, that we can always put that there, which we can obtain by taking 2 to the 5 minus 4 to get 2 to the first, or just 2. So this is an illustration of why property 2 works the way it does. Let's go ahead and take a look at property number 3. So if we have a to the m to the n, that gives us a to the m times n. Why do we multiply this? If I have 2 to the third to the fourth, well, if I had 3 to the fourth, that'd be like 3 times 3 times 3 times 3. Well, here the quantity is 2 to the third to the fourth. So I'm going to go ahead and write down 2 to the third times 2 to the third times 2 to the third times 2 to the third. Now, no multiplication symbols here, but it's assumed that they are here. So we know from rule 1, when we're multiplying common bases together, that we should take 2 to the 3 plus 3 plus 3 plus 3. How many times does this happen? It's 3 times 4. Hence, to get the multiplication that we're talking about over here, which is equal to 2 to the 12th, which is what we'd have. 3 2s, 3 2s, 3 2s, 3 2s, that will give us 12 2s. Okay. Last but not least, we have a times b to the m. Now, we notice we don't have exponents here, and you're going to notice, too, sometimes we're going to combine using rules 3 and 4. If there were an exponent on the inside, we would multiply it. But let's take a look at an example of what this is going to look like. So suppose I have x, y, and that's going to be to the fourth. Well, just like I did with the law number 3, I write xy times xy times xy times xy. And if I do that, I count my x's 1, 2, 3, 4. That will give me x to the fourth. Y 1, 2, 3, 4. That will give me y to the fourth. Hence, if I take 1 times 4, that will give me 4. 1 times 4, y to the fourth, giving me my final answer. What I'm going to recommend that you do, and what I will do in the next video, where I go through examples of these problems, I'm going to ask you to kind of keep this sheet handy. As I work through the problems, you're going to see I'm going to keep this sheet to the right, not showing all the examples, but just the properties, so that as you are doing these questions and as you're putting these in your notes, identify in your notes what property or properties are being utilized to do the questions. So some people, these properties come naturally, and the notation of this is not going to be necessary. But for other people who are struggling with the properties of exponents, this type of work can be very important in helping them do their work consistently. The next video is coming.